All right, thank you and welcome to HKG15-207. This is our continuation of our Advanced Toolchain Usage sessions. So we started these in Burlingame with session 1 and 2, and you can find those on SlideShare. This is a series of discussions and presentations given by Linaro toolchain experts on a variety of toolchain black magic. I tried to come up with a more involved description, but really this is anything from toolchain hacker stuff and toolchain development things to toolchain usage. Any suggestions for future topics to continue this series, you can send to Linaro toolchain at linaro.org. So today we're going to be doing parts 2 and 3.
3 and 4.
Sorry, 3 and 4. This is 3. 4 will be in an hour. We're going to cover as much as we can. We're probably not going to get through all the content as per last time.
And whatever we miss, we'll start from that at Next Connect. So there will be probably sessions 5 and 6 Next Connect.
All right, so here are the sessions. Here's what we're covering. I'm not going to go over this, but those are dynamic links, so you can click those and go right to those slides. So I'm going to be covering some interesting issues with debugging and the dynamic linker. So this is going to involve just discussions of how you debug with dynamic linker issues involved. So if you look at an ELF binary, you will notice that the ELF interp header, program header for an application, has the path to the dynamic linker embedded in the header. What does this mean? This means that when you execute that binary, the kernel looks at that interp header and looks for that dynamic linker and executes that dynamic linker before it executes your application. That dynamic linker is told to load and resolve symbols in your executable. So this is embedded in every executable. So this means you can't really easily change the dynamic linker. You have to use tricks to get a different dynamic linker to execute your application.
Yeah, think of this just as a shebang in hashbang in the
shell script.
In shell scripts, yeah.
So by default, the Linux kernel will invoke this program interpreter to load the application, and by extension, GDB will also invoke that because that's just how it works. This complicates debugging when you're investigating problems potentially caused by an uninstalled dynamic linker. So let's say you're doing glibc development and you've got a bug, and the bug is maybe in the dynamic linker. Good luck finding the bug. So a great resource for this is on the glibc wiki. This has recently been updated by Carlos O'Donnell. This shows all of this in as much depth or maybe even more in depth. That's a page I started a long time ago, and Carlos has updated that to be more recent and more in track with recent best practices. Oops, let's go here. So some common scenarios I want to go over could be debugging the application before application main. So when you call your main function in your C program, that is not where the program starts execution. Your program starts execution in little chunks of code that were statically linked into the application from the system library at link time. So sometimes you need to debug that code. And in fact, I had a bug once where I was debugging this problem because I saw that I had awesome performance. I had an application that had 1,000 times the performance that I expected, and what I found out was that the compiler was branching init directly to Finney, and it was just loading the application and exiting instantly. And I had to be able to find a way to debug the code before main. Another scenario is stepping into the dynamic linkers resolver. So there have been some interesting bugs that I've run into in the resolver, specifically race condition bugs. And you need to know how to get into the resolver. And in fact, a lot of people don't know what the resolver is or how it works. So we'll cover that a little bit. And then finally, you might need to debug the dynamic linker in the glibc build directory. So if you are working on a glibc patch and something breaks, you might need to actually debug the dynamic linker. And that embedded ELF interp header will make it difficult for you to do that. So we'll look at the tricks for getting around these issues. So as I said before, with application main, you often need to debug situations where there's a problem before main. And main is the normal entry point for when you're debugging an application. So if you need to debug before main, you need to find a way to get there, to get where you need to go. So if we look at this application, just to, this is hello world. I'm using puts because the compiler will inline or will replace printf with puts. So I'm just going straight to puts here. So we have two instances, hello world and hello again. So the first thing it does is it starts by debugging dynamic. We want to start by debugging the dynamic linker directly. The reason we want to do this is because we want to break into the dynamic linker so that we can investigate what happens before main. So start the dynamic linker in GDB, put a break on start, and tell GDB to run the dynamic linker with hello world as a parameter. So you'll see what it does is it starts the dynamic linker and breaks on start. Whoops. So if we look at start, it's provided the application by glibc when the application is linked. So this is statically linked code. This is in the text section of the application. This is a conduit to setting up the environment for the application. So this will do things like get your environment variables, get your argv and your argv and your argc, get your aux vector, that sort of thing. So why is this useful? Well, you might need to just debug constructors and destructors. So those happen before main. So if you have a library that needs to have a constructor run on start, you might need to debug that. You might need to debug TLS usage. You might need to read the aux vector or read the environment variables or read arguments before the dynamic linker gets a hold of them. So debugging the dynamic linker in the glibc build directory. Do you remember how the interp program header embeds the path to the dynamic linker? Well, when we're building and testing glibc, the dynamic linker isn't yet installed into the location where it's configured to run. So unfortunately, my slide's off the page. The interp program header will say, hey, here's where we're supposed to debug. But when you're building glibc in the build directory, it's really in a different directory entirely. So if you need to debug it, you need to be able to specify how to get to it. So you need to use the same process as we described earlier in debugging the dynamic linker directly. The difference here is you need to tell the dynamic linker where to find the rest of the not installed libraries. All right, so let's look at an example here. So we've got a glibc build directory here in user glibc build elf ld.so. So we're going to run that and break on start and once again run hello world. So this is pretty much the same way. You're going to need to use the GDB set exec wrapper method here. So what's interesting is that when glibc is built, all the libraries are in its build tree structure. So the dynamic linker is built to believe that all the libraries are in /lib. So in the build directory, they're not in /lib, they're in these weird directories or in the weird directory structure. So you'll often want to say, hey glibc, or hey linker, dynamic linker, the libraries are somewhere else, and that's what that set exec wrapper does. Alternatively, you may use run library path and specify where those libraries will be located. Yeah.
What's the difference between exec wrapper and just use set environment value?
So you can't use set environment because I believe the set environment will modify the environment that GDB is executing in itself and not necessarily just the dynamic linker, so you can have some issues with what GDB then expects versus what the dynamic linker expects. At least that's what Carlos O'Donnell's webpage had described. So I always used to use the run library path. So in fact, I don't really know very much about set exec wrapper, but that's what Carlos uses. So I put it in there for that reason. But he does have a warning about setting env actually on his page. Okay, so this is the interesting one. This is the one I really want to talk about. So stepping into the dynamic linkers resolver. So an application or shared library has a PLT. So this is the procedure linkage table, and this is how you access functions that are outside of your application. They're in another shared library. You don't branch directly from your application into that shared library. There are some major security implications with that. So you branch indirectly via the procedure linkage table. One example would be function pointers or ifunc resolve functions. Oh gosh, I have 1 minute. By default, all symbols in the PLT will be resolved lazily. So this means that all those slots have to be resolved. The dynamic linker at some point has to fill those slots in with the actual address of the remote symbols. You can get around this using LDbind now, but that just does it all ahead of time. So the reason you might want to step into the dynamic linkers resolver is you might need to look up a bug in the static linker and see how it sets up the PLT calling stubs. You might want to look for a bug in the dynamic linkers resolver or attempt to understand why a particular symbol is being resolved versus another one. I'm not going to actually look at the resolver. That's pretty heinous code, but we'll look at what is the situation in the application and how does the application get to where it needs to go. So once again, we'll look at the two hello worlds and hello again example. What we're doing here is launching an application. We're launching this application. And you'll see that first branch and link there. That's to something called putS at PLT. So that's not going to put S out in glibc. That's going to put S within your application itself. This is really a branch to a special chunk of code in the text section. So let's see what that looks like. So we're going to step into that and disassemble it. So yeah, this is a special text section that loads the address of the symbol from the PLT slot corresponding to the putS symbol. So if we look at it, let's see. Yeah, if we look at it, basically what this is saying is I'm going to go in this PLT slot, pull this address out, put it in a register, and branch to the address that's in that register. And what we'll find is if we do that, we can well, let's look at this example. We look at the text section a bit in front of the chunk to see that we have two very similar chunks of code here. These are both pretty much doing the same thing. They're just looking in different spots in the PLT. So what you'll find is for every remote call that you have in an application, you're going to have a chunk of this in your text section. All right. So if we go in there, let's see what value is loaded from the PLT slot for putS. So it's this address 0x4003.0. That is a text section in this executable. Why is it loading a slot? Why is it loading an address from the executable or from the PLT slot and going to somewhere else in the executable? Well, that position, if we look at where that is in the text section, you'll see there's this list. These are all PLT slots, and they're all going to the same spot. And what that spot is the resolver. So this is actually a little chunk of code which gets you into the resolver. So this is a special section of text that loads the address of the dynamic linkers resolver directly. And the very first time you try to access a function that's remote to your application, you're actually getting dropped into glibc's resolver. So the first time every symbol is referenced via this PLT entry, the dynamic linker will first have to locate that address via the resolver. So yeah, so that first putS we call, that drops into the dynamic linker. So if we break on that, break on the second putS. So let's say we did the first one, the resolver ran, and we break on the second one. And we go through these steps again, and we look to see what's in the PLT slot. You'll see that the PLT slot is now the address for the remote IO putS function. So the second time through, the PLT slot now contains the correct address. So every subsequent time you call putS now, you will actually branch to the remote putS function. And this will be done for every single symbol that you, every single remote symbol you call. Now what LDbind now will do is LDbind now will pre-populate the entire PLT with the remote addresses before it actually executes application main. So if you have performance concerns where you're worried about the actual performance of an application while it's running, you might want to bind now early, get all your symbols resolved, and then you don't pay the penalty of lazy binding later.
It's not performance
Yeah, real-time considerations, yeah. All right, so this is the end of my section. I guess we could ask for questions. That's pretty in-depth, but I think the slides walk you through it pretty well. But are there any questions immediately? I mean, this is kind of a lightning talk. All right, well, I'll hand this over to Maxim, and he can go through the next set of slides.
Yeah, so we'll start with a joke. How do you know that you're a toolchain developer? Is that if you start smiling listening to this stuff and it excites you, then you are.
If you're doing infrastructure, you're a toolchain developer.
So, okay, I'll be talking about debugging with backtrace, what it is, and walking through a couple of examples how to use it. It's a nice little tool that is a part of standard C library. It is not used in many applications, but it is very nice debugging feature for several use cases. The best use case is when you want to log critical events and when they happen in your program, to have some context about what was happening in program just before the event. On the large scale, it just gives you the full backtrace, which is what you can get from a normal debugger. But it can either print it out to a console or to a log file, so that you don't have to run the program in the debugger when the critical event happens. Like you have a program crash, and it happens every other year, and you still want to figure out what is the state of the program, or at least something about the state of a program to try to investigate this. But you can't run the program in the debugger for 2 years trying to catch that rare fault. It is very fast. It incurs very little overhead on the normal program execution. So this, to contrast this with sanitizers, when you get very good instrumentation, but at the cost of additional overhead on the whole program when it runs. And it does not have any extra dependencies, so you don't need sanitizer libraries, you don't need debuggers, you just need your normal C library, and then you can use this feature. The constraints of using backtrace is that you need to add code to your application where you to the points at which you want to get a backtrace. So if you want to get a backtrace in your signal handler, you need to add code to call backtrace in the signal handler. You cannot get code in the arbitrary spots, just like the debugger can provide you. And you will need to rebuild your source code. So backtrace is just 3 functions. It is to first function, backtrace generates the backtrace information, and then that information can be printed out in one of the 2 ways. Either it can be converted into strings, or it can be printed out into a file descriptor. You can learn more about it by using standard Unix or Linux documentation. I believe backtrace is POSIX. Yeah, so it should be on all POSIX compatible systems. So we are going to look at the first example when we have assert calls in our application or system library or just user library. We just have a function in our code that we call assert, and we put it throughout our application, which is a good practice. So to add printout of backtrace, in this case, we need to do a couple of things. First, we need a buffer where to store the backtrace. Then we populate the buffer with backtrace information, we convert that to strings, and we print that out. Fairly straightforward. A couple of notes. By default, backtrace will take an argument for how big an array or how big a buffer you give it, and it will generate backtrace for only top n frames in that buffer. So if you want to get the full backtrace, which will, in theory, end at main call of your application, then you need to do that in a loop and increase the buffer until you get the full backtrace. Some applications can have backtrace in the hundreds of frames. I'm guessing that's not uncommon. And especially if you have a bug in a recursive call, you will get a very deep infinite backtrace until you run out of stack. So you want to be able to catch that situation too. Any questions about backtrace so far? Yes, Will.
Does it demangle C++?
Does it demangle C++?
No. So.
It depends. I think it does if demangling is implemented in the C library, which is true for most targets, but not for all. Any other questions about the backtrace? Okay. Any questions about this example? So fairly straightforward code. Normal function, allocate buffer, get backtrace, print it out. Life is good.
There's a question over here.
Yeah?
Does it work with script binaries?
Say again?
Does it work with script binaries?
Does it work with strip binaries? Yes. So the trick here is at previous slide is that you will always get correct backtrace. The difference will be in backtrace symbols and in the strings that it will return. If your binaries are stripped, then you will get raw addresses. If you have symbols, then it will actually look up the symbols and it will print them out and potentially demangle C++ symbols. So it works with both stripped and unstripped binaries. It just depends on what kind of feedback you will get. Prathamish?
If a function is inlined, will the backtrace still report that function in the stack trace?
So if the function is inlined, will there be a backtrace? Normally, no, because when a function is inlined, there will be no separate stack frame. So backtrace works on the level of stack frames. If there is a frame, it will include it in the backtrace. If there is no frame, which is often the case with inline functions, there will be nothing.
Will it work with static functions?
Static functions? Yes. Static functions have their own frames, so yeah.
Often aggressive inlining, you'll get aggressive inlining, so you might see gaps where you would expect functions, but the compiler might have just inlined something for you.
Also,
Yeah.
tail call elimination causing problems.
Yeah. So in particular, if you try to get a backtrace from a dynamic linker that Ryan was talking about, dynamic linker is so heavily inlined, then it's very difficult to figure out in which function you actually are when you're debugging it. So
It's not going to help you with macros either.
yeah.
Wow.
Okay. So the second example, I like a bit more because this is what you can do and play with some real embedded systems. So the second interface to getting symbols out of backtrace is backtrace symbols FD, which instead of converting information, backtrace information into strings, it writes those strings into a file descriptor. And this can be any file descriptor. It can be an stdr, which is the case in this example. it can be a socket into a syslog. So you can connect to a system syslog, and dump all that information there. It can be, if you ship a device like a Wi-Fi router to your clients, your application, your system software can open a connection with client's permission to your error log server, and that will be file descriptor of connection, of IP connection somewhere on the internet, on your machine, and you will get automatic bug crash reports from your clients. So possibilities here are quite good, and backtrace is, I know it is used in embedded systems a lot for this reason. Because sometimes embedded system may not have easily accessible syslog, they may not have console, at least monitored console, and when you can open an IP connection and have a socket and file descriptor associated with it, it can be a real good insight into why your program crashes.
Couldn't you have used std error macro instead of 2 in that function call?
I have a comment. So I would imagine there is, it would not be standard. There is no macro STDR.
There's a macro implicit somewhere.
Yeah, exactly. 5 no, yeah.
Sorry, what am I missing? I don't see the file descriptor.
It's 2.
Oh, 2.
See? Thank you very much.
Yeah. So in this case, we have a very simple code where we bluntly write to 0 address and initialize it properly. And in this case, we will get a signal fault. Why are we using static buffer in this case? Who knows? Who can read the comment? Because we cannot malloc in a signal handler. This is one of the things that we will eventually cover in our Advanced Toolchain Usage. So we need to have a static buffer, and we populate the backtrace and send it off to standard error. So anytime your application will get a signal fault, it will dump the trace, and in this case, it will actually return back to the program. There should have been an abort somewhere around here, so that we would crash.
Is this cross OS?
Yes. So this is pretty much standard code. So, and it compiles and it runs.
I mean, the backtrace symbols FD, will it work in Windows or Mac OS X system? Oh.
Yes. If it is, Mac OS is POSIX, so it should work.
I don't think so.
It is GNU extension?
It's not, I don't think it's
Ah.
It's in
What it makes
Yeah.
Android. Right, so that's,
Yeah, no extension.
yeah, it's a,
Okay.
it's a glibc extension. So if you have glibc, you have it. If you don't have glibc, you may or may not have it. So I don't know about Android. He said it, macOS has it though.
I think
Yeah.
it's in UC-libc as well.
Okay, I'm done.
Couple questions, comments here.
Next one, malloc debugging and tracing.
That's a question. Yeah.
Maxim,
Yeah.
just don't you think actually the last example is not very reliable, because how do you, if you crash with a segv, how do you know actually that it's not like your files on all those tables actually corrupted? So when you try to write actual call actually through this stuff, you can get actually kind of like get actually secondary crash, and that would
In
be
the
actually
signal handler.
quite nasty. And frankly, the backtrace is a great function, but the use case is much more subtle than I believe that the one that you described, because frankly, both assert and 6agv, if you just enable core file collection, that's it. You get the core, you get the full image, and you can debug as much as you want. So all those kind of like running one that if you won't keep running and you're producing the backtrace, that's the one probably actually the most kind of interesting one.
So core dump default is limited. So if you have a big enough application, core will not be dumped. Second point, if it is a remote system which is installed at your client, you need to ask client for that core dump, and they need to extract that from the machine. And third, file system may be read-only. So if you're running from a flash, there is not that much space to dump from read-only flash.
No, but where do you store actually your file? Where is your file, right? So it's arguable, but normally I think actually kind of like backtrace typically used actually in the situation where you produce a backtrace and you keep running. So it's kind of normal execution. When you're crashing, I wouldn't recommend actually to use it, frankly.
Well, depends on what you want to do in your asserts. In asserts, yes, you can continue running. In a signal handler for 6sec-v, better crash. Okay. Well, thank you. Thank you.
I'd just like to cover a couple of malloc debugging tricks that you can use with the standard Linaro toolchain. glibc comes with some more GNU extensions for doing malloc hooking, which lets you install a function that's called whenever any of the allocator functions are entered. This is just a list of them here, so covers pretty much the whole range. The memline hook's called for a bunch of aligned allocation functions like valloc and pvalloc as well. As you can see, they all take a void pointer, which is the pointer to the call site, so that's very helpful if you're going to do some logging or backtracing or whatever you want to do with it. mtrace is yet another glibc extension that's built on top of these hooks. You can set a malloc trace environment variable, which is a file name, and then call the mtrace function, and from that point onwards, every time you enter the allocator, there'll be a trace written to that file. It's actually in quite a legible textual format, although there is a script called mtrace that will turn that format into a leak check, which is reasonably useful. But it's certainly possible to build other tools on top of it. So if you've got concerns about how your heap's growing, you can use this file to sort of bit of Perl, bit of shell script or something to give yourself some quite quick and easy numbers. So here's just a quick example that just does a little malloc, plays around with it, and then quits out. And then what you will get from the mtrace report is this function here, which I haven't actually managed to get it to output symbol names. So it tells you the line number, but it doesn't actually seem to tell you that you're in main, which is a bit sad. mcheck, another GNU extension built on top of these malloc hooks, is basically provided to do heap consistency checking. So if you've got some problem where your heap's getting corrupted, you've got, say, a buffer override that's going into the malloc bookkeeping information, or you've got something like a double free, mcheck will pick that up. You've got to call it before any allocations are done, before the allocator's been entered at all, which can be quite tricky. One way to do it is to build a simple shared object that has an init function that calls mcheck and do LD preload with it, and that'll make sure it happens really early on. You can pass a function. You see in the prototype of mcheck there's an abort function which lets you do different stuff depending on what you want to do when inconsistencies are found. There's an mcheck status enumeration which will tell you what kind of problem it's detected. I'm not sure there's much you can really do besides abort in that hook though, to be honest. So I'm not quite sure of the use of it. There's also a function called mprobe which lets you do consistency checking at any specific arbitrary point in your program, because mcheck itself will enable consistency checking every time you enter the allocator. So every time you do a malloc, every time you do a free, it'll do a consistency check. Whereas mprobe, you could do it if you have a concern about, say, a specific sequence of code. You can just put an mprobe in the middle of it, and that'll do the check then. But again, you need to have called mcheck right at the start as well, otherwise mprobe will either not do anything or crash horribly. So those are a couple of techniques that actually come with the standard Linaro toolchain. There are, of course, other ways to do it, which I'm sure a large number of you are familiar with these things, like third-party debug libraries like dmalloc or electric fence for people that remember it. Valgrind's a really useful tool as well. These things all come with different trade-offs, usually performance versus either accuracy of the detection or the versatility of the detection. Because I mean, Valgrind will detect absolutely any mistake in usage of memory pretty much, but it will take a very long time to do it and use a hell of a lot of memory as well. So I'll not cover Valgrind or dmalloc because they don't come as part of your standard Linaro toolchain. jmalloc and tcmalloc as well, they have some extra little debugging things they can do, but we don't ship those either. But what we do ship is we do ship the address sanitizer as part of GCC, which in theory can spot any kind of out-of-bound reads or writes to either the stack, the heap, or static data. If you want to actually use the address sanitizer, then you have to rebuild your whole application, which is the downside, I guess. Okay, so all the versions of Linaro GCC 4.8 and later and Clang have the address sanitizer. I'd say it will work on the heap, stack, or globals. It only has a performance overhead of 2 times, which is, for these type of tools, surprisingly good. It does use quite a lot of memory, so depending on the situation you're in, it can be useful, or in an embedded system it might be a bit much.
So that is only if you know how to unwind without using the unwind tables. Because if they use the unwind tables, it's 5 to 10 times lower. And the problem with that is because the FP, I think the frame pointer, has an issue, and GCC does that by default, and LLVM doesn't.
So the 64-bit, if you're talking 64-bit,
No, 32-bit.
32-bit, yeah, there is no frame pointer in the API.
Yeah, so, but yes, so there is on AR64, there is on Intel, and you can use it on on ARM v7, but GCC doesn't because of history, and then the sanitizers have to guess, and Clang generates them because it's the same standard on AR32, 64, and ARM v7, and all the others in Intel, so they don't do anything special. And because the API doesn't mandate yes or no, they just say, yeah, whatever. And then the sanitizers have to guess which kind of stack they have, and that has some overhead.
Yeah, well, yeah. I believe the marketing and the PR, so that's what happens. So it's just a quick example of just mallocing a bit of memory and then scribbling in it, and just to test to see if it'll actually work. So you see, as Renato pointed out there, it's best if you put F no omit frame pointer on there, so you can actually get proper backtraces. -F sanitizer equals address is the key step there that enables the address sanitizer, and that's the output there that you get from that bit of code now. So it's pretty clear what's happened. It tells you you've written a write of size 1 past the end of your 10-byte region. So it really couldn't be any clearer than that, to be honest. it gives you really good errors. When it catches things, it gives you really good errors, and it makes it really quite simple to debug. But this was actually the first thing that I tried, and it didn't work. And this is kind of instructive because it explains why, of how Address Sanitizer works and some things that it doesn't pick up. Address Sanitizer works by instrumenting reads and writes and checking against a data structure that tells it whether or not it's a valid place for a read or write to happen. So that clearly means that you have to rebuild all your code to get this instrumentation in it. So if you've got a C library, that's not going to be instrumented. So C library functions may not actually apply this kind of protection.
You're not building your libraries with Sanitizer?
It probably would. I don't know. I don't know if you can build glibc with fsanitize equals address. It'd be interesting to see if it worked. Yeah. It's a possibility, but I didn't actually try that. But what Address Sanitizer does do, it does intercept a bunch of standard calls. So things like memcopy, it intercepts. So obviously that's a really common way of doing memory corruptions, is your memcopy beyond the end of your buffer. So Address Sanitizer will put an interceptor in and catch that.
I would hope it would do that in this case as well, because that's also a very easy way to corrupt memory.
Yeah, I thought that. But it doesn't. That will run
Patch
just
is welcome.
fine. It's possible they've improved it. I mean, I was just using the standard 4.8 toolchain, so it may be that latest versions.
Oh, you're using
do
GCC sanitizers. That's too old. No, you need to get the cutting edge.
But I mean, I guess the problem is that essentially, if they're going to intercept that, they'd have to implement a full GNU compliant smprintf implementation, which is at that point just rebuild glibc. So yeah, it won't catch everything. It will catch a lot of stuff though, and it's relatively low overhead. So it's a useful tool and comes with the standard Linaro toolchain. So it's.
So if Maxim is 0, then it will work, right? 7, 8, and then 0 there, and then that.
Yeah. Okay, is this the next session? Do we have a break now?
We still have 7 minutes left.
Do you want to start this one now, or do you want to pick it up later?
I guess we can take a break.
Okay.
Should we do that? Yeah. There's the next session's in the same room, similar kind of topics. So.
Run away.
We're just going to keep going.